Hey, how's it going, everyone? I just wanted to, sort of do some series problems and sort of see where that would lead. So I wanted to actually pick the hardest just because I thought it would be a good warm up. But apparently we have the summation of n equals 1 to infinity of -1 to the n. Um, Times pi to the 2n over 2, let's see here. So it's 2n factorial. It's 2n factorial. So I mean, this like at first glance, it's probably you'd probably want to use the alternating series test just because you see a -1 to the n out front. That's always sort of a good um, indicator of sort of using the alternating series test. But also on the other end of that spectrum, we see that there's a factorial, right? So with a factorial, usually you'd actually want to use the ratio test alternatively. And let's see if I can get the ratio test up here. So there that is. And basically what the ratio test says, it says, okay, well, take the absolute value of a of n plus 1 over a of n, right? So, when we take the absolute value of this, the -1 to the n, that sort of just falls by the wayside, as it were. So we're actually not concerned about that anymore. And so this is us sort of, this is the absolute value version of this original summation. And so here the idea is to go around and add ones basically to everywhere that you see an n, you're basically adding a one. And that's actually how you get your a of n plus one. So I mean, this whole thing is a of n, right? But now we're dealing with this a of n. So this whole thing is a of n, except we're going around and we're adding a one. So the idea here is that a of n is equal to pi to the 2n over 2n factorial. And then the a of n plus 1, the a of n plus 1 is actually equal to, well, let's see, right? So we're going to start at pi here, and then we're going to go around and we're going to add ones to all the n's. So we have a 2 here. Now the idea is we're adding a 1 to the n, right? So it's actually going to be like this. It's going to be n plus 1. Okay, it's not going to be 2n plus 1 like that. You actually want to make sure that you nest that plus 1 in there so that we can eventually distribute. So, and the same thing goes here, right? So we'll have n plus 1 factorial. So it's not 2n plus 1 factorial. It's 2 n plus 1 factorial, right? And we can simplify our a of n plus 1 here, right? So we have pi, and so we're distributing this like this. We're saying 2n plus 2 over 2n plus 2 factorial. Okay, so basically we have two very clear, this is our a of n plus 1, and alternatively we have our a of n, which is this. Now, what the ratio test tells us is it says, okay, well, take your a of n plus 1, right? Your a of n plus 1, take it, divide it by your a of n. And you're basically taking the limit of all that. So how would that look like? Well, you're doing the limit as n approaches infinity of a of n plus 1. So that means it's this guy here, right? So we do pi 2n plus 2 divided by 2n plus 2 factorial, right? And this is all divided, and I like to put these lines at the end of this longer line just so I can sort of separate out where my fraction is and where my other fraction is. So it says take your a of n plus 1, which I've taken, and divided that by a of n, which so what would that be? Well, we'll have pi 2n over 2n factorial. Okay, and that's basically the idea. So we have this, we had sort of like a complex fraction here, right? It's kind of like a over b over c over d, right? And so it's kind of stacked in that manner. Now, I'm not too sure if you're aware, but the idea here is if you have a over b over C over D, right? And this is sort of the fractional bar that's separating those. The idea here is to do A over B times D over C. So you actually multiply by the reciprocal of the bottom. So you have your top, sure, but then in your bottom, you multiply by the reciprocal. And it looks a little hairy, but that's essentially what we're going to be doing here is we're going to multiply by the reciprocal. So we're going to have pi 2n plus 2, right? Over, so we're keeping the top guy essentially the same, virtually untouched, by merit of this formula thing that I just talked about, multiplying by the reciprocal. And then we multiply by the reciprocal here. So the reciprocal is 2n divided by pi to the 2n. So this is kind of what we want to take the limit of. And what we notice here is that, so these two things, this and this, this term and that term, they look very similar. And this should be a hint that, okay, this, when we rearrange it, is going to cancel out with this. And this, when we rearrange it, is going to cancel out with this. We just need to put it in a proper form. So let's go ahead and take these two off to the side to see if we can sort of use the properties of factorial to sort of cancel things out. So 2n factorial, right? I mean, this whole factorial deal, I feel kind of gets people confused. The idea is that, if you have n factorial, then n factorial, and that n could be anything. It's n minus 1, n minus 2, and then n minus 3, and then so on and so forth, right? And I think that, so it's n minus 3, and then it just keeps going on and on and on. Now, what if your n was, let's say, n plus 1 factorial, right? Well, n plus 1 is now acting as the new n. So what did we do with n factorial? And actually, I should probably say that before going through this pattern of doing n minus 1, n minus 2, n minus 3, you actually put n down, right? And then you do n minus 1, n minus 2, n minus 3, and so on. So you actually have to put n down. And so we'll do the same thing here with n plus 1 factorial. We'll put our n plus 1 down, n plus 1 factorial, right? But we don't actually have the factorial. So we do n plus 1. Then we do n plus 1 minus 1. What is that? That's just n. And then we do n plus 1 minus 2, right? So that's n plus 1 minus 2. That's n minus 1. Then we do n plus 1 minus 3, right? That's n minus 2, right? And so you can see that basically everything after n plus 1 is just n factorial, right? Everything after n plus 1 is just n factorial. If n factorial is equal to n times n minus 1, n minus 2, n minus 3, well, I see that this pattern n minus 1, n minus 2, n minus 3, it's going to continue here on out, right? So that means n factorial is just equal to n plus 1 times n factorial, right? So if I ever saw, let's say, n factorial over n plus 1 factorial, I'd say, well, I know what happens here, right? I have an n factorial on the bottom. I know n plus 1 is just n plus 1 times n factorial, right? And these would cancel out, and I'll be left with 1 over n plus 1. And we're doing much of the same thing here, right? We're trying to apply the same pattern, actually, right? So let's see what happens, right? So I'm going to take my 2n factorial. Remember how I just put the n down? I'm going to take the 2n. Okay, that's my first factor. Then I do 2n minus 1, right? Which is this. Then I do 2n minus 2, right? And then I do 2n minus 3. And then this goes on and on and on and on and on. And I do the same thing with this factorial in the bottom as well. And this was a factorial down here, right? That's carried over from here. And so this is 2n plus 2, right? I just put my n down. And then on my first one, I do 2n plus 2. I do 2n plus 2 minus 1, which is 2n plus 1. Then I do 2n plus 2 minus 2, which is just 2n. Then I do 2n plus 2 minus 3, which is 2n minus 1. And then I do 2n plus 2 minus 4, which is just 2n minus 2. So you can see that everything after this point is just this. It's just 2n factorial, right? So like what I'm trying to say here is that this whole area here is 2n factorial, and it is also here. And it's going to keep matching 2n factorial there on out. So all of these sort of cancel out, right? And the only thing that remains is this, is 1 over 2n plus 2, 2n plus 1, right? So that's the idea, right? So you could either say this as this is 2n factorial over 2n plus 2 factorial. Well, we now know that 2n plus 2 factorial is just 2n plus 2 times 2n plus 1, and then the 2n factorial starts, right? So these kind of cancel out, and we're left with this. So that's our first property here, which we leveraged. And what we see is that, you know, this and this, they cancel out, and we are left with 2n plus 2 over 2n plus 1. So 2n plus 2 over 2n plus 1 in the bottom. Now, what do we have here? Well, so let's do the same thing here. We'll isolate these guys, the pi to the 2n plus 2, right, over pi to the 2n, right? So what can we do here? Well, remember that, you know, if I had, let's say, a to the, let's say 2n minus 1, or actually that's probably a bad example, but all I'm trying to say here is that this top guy can be separated as 2n times pi squared. Why is that? Because when you multiply them, you add the exponents, right? So if you add them back, you get 2n plus 2. So if I had, like, let's say pi to the 3n minus 3, well, that's just pi to the 3n times pi to the negative third, because when I add them, I do 3n plus minus 3, which is 3n minus 3, and then I get this back. And this works for everything. If I had, you know, x to the 4, I don't know, n minus 1, well, that's just x to the 4n times x to the minus 1, because when I add them, I do 4n plus minus 1, which becomes 4n minus 1. So I get the original back. So I broke this up in the same way. I said pi to the 2n plus 2. I said that was pi to the 2n times pi to the 2. And then in the bottom here, I have pi to the 2n. So these cancel out, and I'm left with pi squared, right? And that's in the top, right? So I cancel these out. We can see this one is remained in the top. How do I know this is in the top? Well, when I solved this guy here, it was 1 over all of this. But when I solved this guy here, it wasn't 1 over anything. It was just pi squared. So that's the idea. Now you could FOIL this out, but it doesn't take too much guesswork to see what's going to happen here. We have a constant. We have a constant in the top, and once you FOIL this out, you'll have like 4n squared something something something. You'll have a polynomial. So the denominator actually has a greater power. So you have a constant over infinity, kind of, which we know is infinity, right? So the whole thing goes to infinity, and therefore the series, this series here, diverges by the ratio test. So let's see, because it's greater than 1, and if it's greater than 1, then it essentially diverges. And I think that's apparent if you look at a formula sheet. It diverges if it's greater than 1, and so this is definitely greater than 1, and therefore this diverges here. There were some other questions as well. I thought those were pretty neat to look at. let's see here. We'll go to this one. So let's see. So what do we have, right? We have n equals 1 to infinity of 1 over n cubed, right? And this is actually plus 1 over 3 to the n. Now, I'm not too sure if you're aware, but the idea is that if you're adding series like this, you're adding, if you have a series and you're adding two things, you can actually break this into, like two different, two different series. It's the addition of two. These are kind of like now they're their own series problems, right? And so now you have to solve these individually and see what happens. So you're looking at this and you're thinking, okay, well, this is a P series, right? Why do I say it's a P series? Because it matches that form, right? If I go to a P series, 1 over n to the P, right? This is like 1 over n to the P, but the P is 3, right? So what does the P series say? It says if the P value is greater than 1, then you converge. So this basically, this part we know converges, this part, only this part. When we look at this here, what do we notice? Well, we notice that it's geometric. Okay, this is kind of like AR to the n. Now, how does this look like AR to the n? Well, I'll tell you, right? So you have your series here, and you have infinity, and you have 1 over 3 to the n. Well, 1 over 3 to the n is the same thing as 1 to the n over 3 to the n. Why? Because it doesn't matter what n is, it will always be 1. If n is 5, if n is 6, if n is 7, doesn't matter, it will always be 1. So this is the same thing. And if this is true, then I can rewrite this as 1 over 3 to the n. So I'm bringing this power out up on top, and it's 1 over 3 to the n. And my a value is 1 here, right? So this is my r. So they say take the absolute value of your r, and if it's greater than 1, well, let's see what the geometric test says. If it's greater than 1, then you diverge. If it's less than 1, then you converge. So this is 1 over 3. Now, if you're unsure, 1 over 3 is actually 0.3, which is less than 1. And if it's less than 1, then we converge. Yeah. So this basically, this whole thing should basically converge. We have 1 over 3 to the n, and 1 over 3 is less than 1. So by the geometric series test, this converges, and this also converges here. And this question doesn't seem to ask us to find out what it converges to, but it does want us to like say whether it converges or diverges. Now, it would be difficult to see what it converges to as a whole. We can find what this converges to, but the P series doesn't let us, say what it converges to. Let's look at this one here. So we have so this is 1 over under root n minus 1. So this is a good contender for the comparison test. And you're just looking at this, right? I mean, how did I know that? Well, the idea here is like, okay, well, it's not geometric. It doesn't have anything to the n power. It's not just, it's not a P series, right? It's not just like something like this. Integral tests may work, who knows, but let's try to avoid it if possible. It's not alternating, right? Because it doesn't have a -1 out front. And it's not the ratio or the root test. We don't seem to notice any factorials. So that leaves one of the comparison tests. Now you can try both, or you could just try, whichever one you want. But the A of n, right? The A of n would just be the original, which is this. And then the B of n. So the B of n, how I usually get to the B of n is I strip away all the constants, right? So I have my B of n like this. I stripped away all the constants and I just have this. Now remember that like under root n is the same thing as n to the 1/2, right? So this is kind of like this, right? I'm just making that apparent. It's like to the 1/2. Either way, however you want to see it, that works. But what the comparison test says, and it's, you know what, it's probably best to just look at it like this, right? But what the comparison test says, or the direct comparison test, it basically says that, if your A of n is less than your B of n, so first let's figure out which category we're in. Is our B of n greater, or is our A of n greater? Well, I'm subtracting things from the bottom. So if I subtract from the bottom, then my fraction gets bigger. So which means this is bigger, right? So I'm looking at this one where A of n is greater than B of n. And if A of n is greater than B of n, then basically the series will diverge if B of n diverges. Now the question is, does B of n diverge? Well, as a series, does B of n diverge? That's the question. And this is where it becomes useful to write this as n to the 1/2 so that we can use the p series on it. Now, what the p series test says, that it says that if you're less than 1, then you diverge. So basically, this basically diverges, right? Because this is raised to a power that is less than 1. And the direct comparison test says that if your A of n is greater than your B of n, and your B of n diverges, then your A of n will also diverge. So this is basically a divergent series, just because of the comparison test. We took we took the A of n, we took the B of n, we stripped the constants down to get to the B of n, right? And then what we are asking ourselves is, okay, is which one is bigger? And since we're subtracting from the bottom in one of them, they're both pretty much the same. But since we're subtracting one from the bottom in one of them, that fraction would become bigger. Now, if we were to add in the bottom in one of them, then that one would be smaller. And so that's the idea here. So A of n is actually the bigger fraction. And we know that if it's the bigger fraction, let's see, if it's the bigger fraction, then B of n must diverge for A of n to also diverge. Now, if B of n converged, then this test would not be applicable. But since it diverged, it is applicable. Let's see what else we have. So this is, okay. So it seems like we have 1/5. Let's see here. Now, the idea here is basically to come up with a formula for the series. Now, this isn't a sequence, right? This is in a sequence, you'd just be listing things off. This isn't a sequence. This is a series. And because it's a series, so we basically come up with a formula for the series. And then we use whatever testing method we can to figure out if that converges or diverges. Now, the thing that I recognize most here is that we're we're increasing by 2. So it's kind of like it's 2n, right? For every n value, it's like up with a factor of 2. But the problem is, and obviously the numerator sort of just stays the same. But the problem is, my first element, if I plug in 1 in here, it's actually 1/2, right? I mean, that isn't my first element here. It doesn't match, is what I'm trying to say. And so maybe what I can do to offset this is just add 3 to it, right? Because then I get my first element. If I add 3 here, I get my first element. And then you'll see that everything just sort of fits that pattern. So if I plug in 1, I have 1/2 plus 3, which is 5. If I plug in 2, I have 1/4 plus 3, which is 7. If I plug in 3, I have 1/6 plus 3, which is 9. And so, I have my series here. I just need to figure out whether this converges or whether this diverges. And again, whenever I feel like I could strip off constants and stuff, I usually go for the comparison test, right? So I have my 2n plus 3, and my B of n is just basically my A of n, except I strip the constants off, right? So it's 2n. And I clearly see that I'm adding stuff to the bottom here So this fraction is actually going to be smaller. So it's kind of like this here, right? It's going to be b of n. And so what the comparison test says is that if the direct comparison test, at least, it says that if your b of n is greater than your a of n, which is in this case we have, then your a of n, I mean your original will converge basically only if your b of n converges. Now what we notice as a series are b of n 1 over 2n. This is a p series. Why do I say this? Because you can pull that 1/2 out front, and then you have 1 over n. Now, the p series basically says that if it's less than or equal to 1, then you diverge. So this does not converge. The b of n does not converge. The direct comparison test was telling me that if your b of n is greater than a of n and your b of n converges, then your original converges as well. But in this case, the b of n does not converge. Instead, it diverges because that's what the P series told us. So this is a non-conclusive test. I can't use this test to figure out this series. So, but again, I mean, like what test do I use now? It's not alternating. I don't see a -1 out front. And it's not a, let's see, it's not a alternating series. It's not because I don't, like I said before, I don't see a negative. It's not a ratio test because I don't see factorials. It's not a root test. It could be an integral test. In fact, probably that would work with a u sub maybe, but let's avoid that if possible. It's not geometric because we don't see anything raised to the power of n. And it's not a direct comparison test because I just tried that, but the limit comparison test may work. So basically what the limit comparison test says is, take your a of n, take your b of n. We already found those. We already know what those are, right? But this time we're not judging whether they're greater or smaller. Instead, what we're doing is we're adding 1, or rather here, we're doing a ratio between them. So we're taking the limit as n approaches infinity of the a of n over the b of n. So the a of n is 1 over 2n plus 3. And the b of n is 1 over 2n. And remember what I said before, that like, you just multiply by the reciprocal. So that's 1 over 2n plus 3 multiplied by 2n, right? What is our limit here? The limit as n approaches infinity is 2n over 2n plus 3. And we know that if when we're taking the limit of things where the the top exponent is the same as the bottom exponent, that's just equal to the division of the coefficients. The division of the coefficients here is 2 over 2, which is equal to 1. So basically the limit comparison test says that if a of n over b of n is greater than 0, then they either both converge or they both diverge. So we know that b of n as a series diverges. We proved that over here, which means that the original must also diverge, which means this is a divergent series. So let's go to, let's see here. Let's go to this one here. This one is basically saying if you have n equals 1 to infinity of 2 to the n plus 4 to the n over e to the n. Now, a very common theme is here in questions like this, sometimes people, they say, okay, well, I can sort of take this n out, and this is 2 plus 4 to the n, right? And if I bring it back, then it would look like that. But this is not the case. You actually can't do this with addition. And try to see that yourself. What if n was 2? What if n was 2? Is this, is doing this equal to this? No, it's not, right? 2 squared is 4 plus 4 squared, which is 16. 16 plus 4 is 20, okay? And then here you have 4 plus 2, that's 8. 8 squared is 64. So clearly these are not the same thing, so we can't actually do that. But another thing is that, if you have a over a plus b over c, what you can do is you can do a over c plus b over c, okay? But you can't do this if you had c over a plus b. You can't do c over a plus c over b. This is not allowed, but let's see. Yeah, so this is allowed. But this is not allowed. Okay, and so here we clearly have the A plus B type over C. So we can separate that out, right? We can do n equals 1 to infinity of 2n over e to the n plus 4n over e to the n, right? It's a common denominator. That's how you can remember this, is if there's a common denominator, then you can split them up. But here there isn't a common denominator, so you actually can't split them up, right? So here there is. And again, right, so in this case, we can pull that n out. That's 2 over e to the n plus 4 over e to the n. So while doing something like this is not allowed, doing something like this, a over b, and if they're both raised to the n, then you can do a over b to the n. This is allowed, okay? But doing something like that is not allowed. And here again, we have an addition of two series, right? So we can do n equals 1 to infinity of 2 over e to the n, right? Plus, and then we have another series here to infinity 4 over e to the n. And I mean, at this point, you just have to, this is a geometric series. You're looking at it, this is a geometric series here. You have an r to the n, right? This here is your r, these are your r's. And you have to see whether the absolute value of your r is greater than 1 or less than 1. And we notice that, we have, so is 2 over e greater than 1 or less than 1? Well, you can actually, you can see that it's less than 1. So this converges by the geometric test. And this one, 4 over e, let's see what happens here. It's greater than 1, so this diverges. So which one is it going to be? Is it going to be convergent or divergent? Well, the idea is that, let me ask you this. What's infinity plus 1? It's infinity, right? So you can kind of think of it like this. This is infinity plus some constant, right? So the whole thing basically diverges. We have another one here, n equals, or actually in this case, it's actually k. K equals 1 to infinity, k squared over k squared minus 2k plus 5, right? And we just want to see if, if it converges, then we want to figure out to what value it converges. And so we can basically use the divergence test here. I mean, it's not geometric, it's not alternating, it's not ratio, it's not p-series, it's not root, it's not, so we can use the divergence test. In fact, you should probably be using the divergence test for every one of these before continuing onward. But the idea here is that if you take the limit as n approaches infinity here of k squared over k squared minus 2k plus 5, this is equal to 1, right? Because when your exponents are the same, you do the division of the coefficients and you get 1. And the divergence test basically says that if the limit is not 0, then you diverge. So this one diverges. And that's why we don't even have to figure out what it converges to, because it diverges. If it converges, find the limit. So basically, you have a sequence here. Now, this is not a series. We're not talking about series anymore. We're talking about like cosine of n pi over n plus 1. Now, the thing about like a sequence is if you're given a sequence and you want to know if it converges or diverges, then you take the limit of the sequence as if though it were a function. And once you take the limit of it, if it converges, then your sequence converges. If it diverges, then your sequence diverges. So basically, we have to do this problem. Now, there was a theorem where if you have something like this, if you have a sequence inside a function, then this is actually equal to just doing the limit. Okay, so you basically do the limit of the inside and then you evaluate that at the function. So the limit of the inside, well, what is the limit of the inside here, right? Well, think about it this way, right? Pi is a constant, so we can pull that constant out front. And then you have n over n plus 1. We know that the powers are the same, so it's going to be the division of the coefficients, which is 1, but then that pi is out front, right? So it's actually just pi. So we're asked what is cosine of pi, really? And cosine of pi, if you're not aware, pi is here at 180 degrees, and the cosine of pi at that position is -1, and that's something you could Google as well. So that's the limit, it's -1. For sine of n, right, you're given a of n equals sine of n. And the idea is the same. If you take the limit of the sequence treated as a function, and that will be, so your sequence will converge to that value. So if it converges, that is. So you're basically doing this, right? Now, I mean, like you can look at a sine graph and see that as you keep going this way, you keep jumping between values, it's oscillating, it's divergent. And if you wanted to like, well, I mean, I think that pretty much concludes that. It's an oscillating function, it's divergent. These are, I guess, like stuff we skipped that we won't do. True, false, if a of n converges, then so does a squared of n. I'd say true in that regard. If you reach a finite value and you square it, then it's still going to be finite, I believe. If you have a series that produces a finite value and you square that, then it should be I mean, I think this is up for interpretation. I think so. I'll check into this later. This one is clearly alluding to the comparison test. You can see like the formula kind of matches this here, where it says a of n is greater than 0. So what this is trying to say is it's trying to say, okay, if a of n is less than b of n and b of n diverges, then a of n must also diverge. But what do we see here? We see that if a of n is less than b of n, just like it's saying in the problem here, then b of n will, and b of n converges, then your a of n will also converge. But this one is saying that if your b of n diverges, then your a of n will also diverge. If your b of n diverges, then your a of n will also diverge. So the question is this true? If a of n is less than b of n, and the b of n diverges, yeah, see, the thing is that it's saying if a of n is less than b of n and if b of n diverges, but here we have if a of n is less than b of n and b of n converges. So this clearly is not sort of matching, right? The inequalities aren't matching. Like you could try to compare it with this one. It says the theorem says that if b of n is less than a of n, but this one it's saying that a of n is less than b of n. So this is definitely wrong, right? What about this one? It's saying that if the summation of a of n is convergent, then the absolute value of a of n is also convergent. Now, I don't know if you know that, like, so the idea here is that there is something called conditional and absolute convergence where sometimes if you take the series of something, you can converge, but then if you take the absolute value of that, you can diverge. And then that means it's conditionally convergent. The condition is that you diverged if you took the absolute value. So this isn't the case, right? There have been many examples where you can take the absolute value of something, and it will give you a different result than had you not taken the absolute value for it.